All right, dude, we are live. What's up, guys? This is Dem Keys, and today we are going to continue learning about async Rust programming for the ESP32 using the Embassy framework. So, before we get into it, what have I been up to between yesterday and today? I didn't really do too much in terms of uh, producing clips because I do have a couple of clips. Um, I have I also posted like a screenshot of the code that I was working on for the content pipeline. And yeah, I think I was busy reading some of the other stuff. Oh God, okay, we are dropping frames right at the beginning of the stream. Okay, give me a second. Let me help this stabilize, hopefully. Okay, I think we're better now. Hopefully, we're better now. I think so. Yeah, yeah. Okay, so I was there were a couple of conversations that I was having with Gemini about various topics because I was really curious about um, how ghost interference or ghost frequencies work when it comes to RC electronics or RF electronics, which includes RC cars, remote control cars, and I'm mainly talking about the cheap cars. Now, when I asked Gemini initially, all this time I'd been thinking that RC cars, the cheap RC cars, they operated on the 433 megahertz frequency, which is apparently a very common frequency amongst home appliances. A lot of different types of home appliances operate on that frequency. And then when I asked Gemini, then Gemini was like, actually, the cheaper ones, they operate on like 29 megahertz, and I think there was one in the 40s as well, but not in the hundreds. That's what Gemini said initially, and then I decided to um, look it up myself, and then I asked Gemini again for like clarification because I was getting a lot of different types of information. Like I was seeing threads on Reddit, for example, where a person was mentioning that a lot of the stuff that they're seeing these days that includes RF, it's all in like the 2.4 gigahertz range, so not even in the megahertz range anymore. And then that's when I asked Gemini that, okay, so I'm seeing this information. What's going on here? Was I wrong to assume that there were the cheap RC toys? They were operating in the 433 megahertz range. And then I also found out through Gemini, but also through other people, that in the past decade, a lot of manufacturers have largely moved on from that old 29 megahertz frequency, and a lot of them are either on 433 megahertz or 2.4 gigahertz. So a lot of them have actually moved on to the gigahertz range, and they're not even operating in the megahertz range anymore. Mostly because even the gigahertz range devices have become cheaper to manufacture, and additionally, with like gigahertz range devices, they are often able to print the antenna as a trace on the PCB itself. So I mean that other than that, there are a bunch of other reasons as well. But yeah, it has become pretty cheap for manufacturers uh, to manufacture these 2.4 gigahertz circuits, along with some sort of microcontroller, purpose-built microcontroller that's going to be processing the data that's being sent out and being received back. And the advantage is that with 2.4 gigahertz, you have a lot more, there's a lot more lanes to operate in, and there's a lot more niceties that you're able to get because of the way that a lot of the RF communication happens on 2.4 gigahertz versus how communication was happening on 430, 433 megahertz versus how it was happening on 29 megahertz. Like on each of these frequencies, the communication was happening in a very different way. And 29 megahertz was very, very much perceptible to interference and ghost frequencies and stuff. So it could very well pick up a frequency that it either misinterprets as one of its own. Um, and so, it takes an action based on that, like, moving the car forward, for example. Or it actually gets a signal that is meant for, devices like it, but the, the signal is coming from a different remote, for example. Um, so you would have these kinds of issues with, the lower frequencies. And I was concerned that maybe I got that part wrong, that maybe I got the frequency range part wrong, but it turns out no. It's kind of a mixed thing, because a decade ago, more than a decade ago, you had like these 29 megahertz frequencies running, but over the years, it became cheaper for them to start using 433 megahertz, and then it also became cheaper for them to start using the 2.4 gigahertz circuitry. Um, so yeah, I was doing research on that. I've also continued my Git refresher course kind of thing. More specifically, I wanted to refresh my knowledge on various Git concepts that I've explored before, but I haven't really used them as much. Stuff other than, the simple staging and committing. I'm talking about stuff like um, remotes. Remotes is actually where this whole thing started. The whole thing of me wanting to kind of refresh my knowledge, because there's a lot that I did not know about remotes. Um, Let me open up that Git interactive thing. Hold on. Actually, two things. I'm going to open up two things. And this is what I'm going to be focusing on after today's stream. I'm going to focus on the Git thing. I'm going to. Oh, I also realized that I forgot to post today's clip. So I'm going to have to work on that as well. Fortunately, the clip is, there. So I don't need to worry about not having a clip to post. I just need to come up with a caption for it, and then post it. And what was I? Yeah, okay. So I'm gonna switch to BRB real quick, and also let me let me open up my chat on my phone. Did I switch to BRB? I did. Let's okay. Google Git basics. So this is our documentation. And then I also want the Git interactive, Git tutorial interactive. Where was that hosted? I can't remember where exactly it was hosted. And it was from the Git website itself. They were giving the information for this. Hold on just a second. Okay, let's open up Learn. Under Learn, um, okay, Community, Learn, cheat sheet, the most common Git commands with diagrams illustrating the difference between so and so. Wait, this is new. Hold on, I didn't know about this. Okay, okay, all right. Um, Git immersion, a guided tour that walks through the fundamentals of Git. Let's open that up. Official Git tutorial. Diving deeper. Okay, okay. There was a very, very useful um dude, you know what? Okay, we're gonna try this. There was a very useful interactive kind of thing. I can't remember specifically which website it was. It was hosted somewhere, but I can't remember where the thing was located. Also, I'm seeing a couple of links here. Git repo hosting. Oh, okay. Okay, so I found this thing. I'm gonna open this up. I'm just gonna switch back here and let me also just a second um do this and this. Okay, also right now I'm going through this thing, right? Dude, I need to set up that OBS Rust program that I wanted to work on. I need to set that up like quick because I am running into so many different situations where I would like to, increase the size of the browser window and temporarily make it something like this, for example. Um, but then I have to do this manually and then, later on take the size back down again manually. So, yeah, yeah, okay, whatever. So I found this thing. I was looking on the Git website. I cannot seem to find the interactive thing. I don't know if it's like still hosted or okay, videos, courses. Yeah, I'm not sure where it went. It was a very neat um interactive sort of thing where you had like a I don't even know what to call it. It was an interactive experience where various Git commands were listed out all within like the same screen, and you could hover over a specific one and it would give you a bunch of information, and it also divided up those commands into the various workflow stages, so at which stage you might be using a certain command. It was very useful. I can't seem to find it now, but now there's this thing called Git immersion. So let's take a look at this. Git immersion, a guided tour that walks through the fundamentals of Git, inspired by the premise that a thing is to do what? Oh, I'm sorry, I'm not reading this properly. Inspired by the premise that to know a thing is to do it. Okay, all right. Git is a powerful, sophisticated system for distributed version control. Gaining an understanding of its features opens to developers a new and liberating approach to source code management. The surest path to mastering Git is to immerse oneself in its utilities and operations to experience it firsthand. All right, let's start. Okay, set up set up Ruby. Okay, you know what? Um, I at this point I already know the basics of Git. I need to go into the more advanced stuff. More specifically, let me show you what I'm trying to focus on right now. So I'm here in Git Basics. Um, First, there was undoing things, which I was playing around with this today. It's the concept of reverting and resetting. Resetting actually helps delete commits. There's different types of resets as well. You have a soft reset, a hard reset, and a mixed reset, and each one of them does a different thing. Actually, I think I can show it to you um, somewhere here. I need to find a suitable place to. Okay, do I have um, Rust Proj? Yeah, I do. So let's open up Git UI. As you can see, I've made some. There's only one commit, so I'm going to commit all of this. What is Why do I have this stored here? Yeah, I can't remember why this is stored here, but anyways, I'll commit this. We'll call it second commit, and we'll commit the thing. Okay, so now we have two commits here. Um, is this visible? I think it's visible. Oh, you guys can't see what's at the bottom. So at the bottom of the screen, there's a bunch of options being given. It's being cut off because, well, actually, hold on. Yeah, it's being cut off. But yeah, there's information at the bottom, and in that information, it gives two options. Well, it gives a bunch of options, but two of the options within that are revert, which is I believe Shift D. So this is how we would perform a revert. Um, and and additionally, there is an option to reset, which is hold on, let's abort this. Reset is Shift R. This is a reset, and you can decide what type of reset you want. Like I mentioned before, there's multiple. There's soft, which is it keeps all the changes but stages and stages the differences. So it's basically just undoing whatever changes have happened up until that point. In this case, I should do the reset here because we are resetting to this point. So if I come here, you can see there's nothing unstaged. There's also nothing staged. So there's nothing to commit, right? If I select this and Shift R, so it says that it's going to reset to so and so. So if I choose to do this reset, if I confirm it, now you can see we have changed to this, and now the head is pointing here. A good way to check where the head is pointing, um, Rust Proj, dude, I love Zoxide. It is so useful. Holy shit, it is so useful. Speaking of useful stuff, Siri, this is another very, very useful application. So you can see there's only one commit here. The coloring on it looks a little weird, but this is the, what do you call it? This is the only commit now. There's only the first commit. Um, for the sake of showing, I could. Oh yeah. Also, now you can see the changes have been reverted back to this. So the commit is gone, and the stages have been the changes have been staged. I can unstage everything as well. So I can hit A, and now we are back to square one. I could have also reverted. Right now, I reset it. I think revert limits you to the previous um, the previous commit. Reset allows you to jump back to, you know, whatever other commit you want to jump back to. I should look into the difference between revert and reset. Revert versus reset. Okay, the primary difference between git revert and git reset is how they handle the project history. Oh, actually, I forgot. Hold on. Git reset actually jumps back to the previous commit, right? So the other commit, I'm assuming, is just gone now. So if we look here, there's no there's no second commit. Let's recommit this again. So let's say second commit. Okay, we've committed this now. I'm gonna do a revert, and actually gets this revert gets committed. So here I would need to commit this. How do I commit? Hold on, down here. Okay, so this is what it looks like. So we would be committing this revert change. So if I come here, you can see it reverts back to that change. And if we look here at files, you can see that the file that was there previously is not there anymore. Um, where I think the file is just gone at this point. Yeah, there was that extra file in there. The file is just gone. Of course, I can also, now keeping that in mind, so if we look at this and look at the files in this, you can see there's something called xclip, right? Um, there's no xclip in the reverted version, um, because this reverted back to first commits state, let's say. So you can see here it's removing this. And at this point now, if I take a look at the files, the file is missing. So what we can do is we can reset back to this using Shift R, and we'll keep all the changes. Okay. That's interesting. The file is not there. The file is not there. In this case, the file is just gone. I think it might just be the file changes that take effect. I was expecting the file to come back. Um, but yeah, good to know. Good to know. So okay, I definitely need to explore this a lot more, reverting versus resetting, because there are situations where I might want to, revert back to a different commit. But this thing is, wait, I need to try and understand this. So it reset from that reverted commit. Oh, it reset from the reverted commit back to first commit. Though if it reverted from that commit back to the first commit, then why is the file not there anymore? This is something worth exploring for me. Hold on, I was supposed to open up my chat. Give me a second. Hold on. Okay. All right. Yeah, so this is something, this is good because this gives me something to explore now. Um I'm trying to understand this. So revert allows us to revert back, but then it writes the hold on, let's do something here. There's no change to, you know, add in here. Um let's open up Yahtzee, and let's actually I don't think I need to open up Yahtzee. Let's add in, let's say, echo abc into sum01.txt. So this is our file. Okay, we'll stage this and commit it. We'll call it second commit. Then echo def into sum02.txt, and we will commit this as well. Third commit. There was something that I was going to test out here, and I can't remember what that was. Was it that I was going to revert? Oh, I think I was going to test and see if I can revert back to this. That's interesting. Back up. Shift F shows files. Okay. Revert is Shift D. All right, so we are reverting back to this. Holy shit, there's so much here. This is unstaged. Um, give me a second. I'm trying to figure out how to go down. Um, there. That was crazy. Okay, so this is revert. So we are reverting back to that, right? So let's commit this. Revert first commit. This reverts commit so and so. This reverts commit. Hold on. No, no, no. No, no, no. Wait a minute. This is reverting the commit. So the changes here are basically that all of this is gone. All of this will be gone. The thing will be empty. Let's commit it, and then I can reset it. Um, okay, so let's commit this, and now we only have these two files. So I think I think I have the wrong understanding of what reverting is doing. Yes, okay. You know what? I take that back. Reverting and resetting. I need to look into how both of them are working. I also just realized that you guys cannot see any of what I was just doing. My God, dude. That is crazy. That is crazy. I've been doing this shit for the past, like, I don't know, 10 minutes, and you guys cannot see any of it. That's crazy. Anyways, let's reset this. It's resetting to this. Now we need to reset to this. Actually, we don't need these changes, do we? We can unstage these changes. Do they show up here? Right. We can unstage these changes. Um, how do we remove them? So we're not trying to do ignore, though it would be interesting to see if wait, let me add something here. Wait, okay, we'll test out the ignore thing because I want to know if ignore makes it so Git UI automatically edits the git ignore file. But for now, I need to reset this. Confirm file reset. Okay. 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 I think we are good. Right. Now let's create um, GHI. Sorry, let's create some O3 and write GHI into it. And we have a change here. Let's hit I. Oh, there you go. Dude, that is convenient. That is convenient. I did not know that Git UI could do that. This is definitely convenient for the future. Holy shit. For now though, I guess we can remove that. There you go. Cool. Awesome. Right. So like I was saying, there's a bunch of Git related stuff that I need to explore. Right now we are looking into the, revert and reset thing. But more specifically, I'm interested in remotes. Like this entire thing, me revisiting um Git commands again. It happened because I wanted to look into remotes, because I have basic Git knowledge of, staging files and committing files and also creating branches. Um, but when it comes to, and all of this is fine for when you are working with, you know, um, a simple a simple repo that doesn't have like a central repository somewhere. If it's just one, you're just using it as a essentially a backup system, essentially a version control system, and everything is happening within that repo itself. There's no copy of the repo. There's no like clone. There's no central repo from which you have actually cloned this repo. There's nothing like that. This is the main copy. And all of your work that you are doing is this within this copy itself, which is fine for a lot of situations. It works out just fine because that's your entire backup system, right there. And I mean, I'm using, commands like reset. Commands like reset are you should use them sparingly because as you can see, with something like reset, you could actually like um, you can overwrite history or erase history for lack of a better term. There was a way to undo commits. I don't remember too much about how that worked, but there was definitely a way to undo. I should look into that. I don't know if it's undo or if it's just editing the commit. Let's see what reword does. Yeah, okay, we can edit the commit. Oh, okay, let me reword this. Edit it. Okay, all right. So it edited the thing. Details, branches, tag, checkout. Okay, okay, okay. Right. All right, you know what? We are 33 minutes into the stream, and I think this is a good time. Should we do embassy stuff, or should I just continue reading? What do you call it? Should I just continue reading Git stuff? Because I'm going to be doing this off stream as well. Because there's a couple of these concepts that I want to revisit. Okay, so here's my thing, right? Here's Oh, voice crack. Holy shit. Here's what I wanted to do. Um, so I have Git repos for various projects. Okay. Let's look at this. This is the project. Okay. The repo for this project is within the directory itself, within the root directory. All right, great. The repo is here. This repo is controlled by the version control system. And through this, I'm able to look at all of these commits. And I have essentially backups of Sorry, got distracted. I have essentially, backups or revisions of previous versions. That's through the commits. That's what the version control system does. It allows you to jump to different versions, keep track of different versions, and manage different versions. Um, so this is one copy, right? Let's say this project. This is one copy. This is right now the only copy of this project. What I wanted to do is I wanted to have a central location. I still haven't decided which of my machines I want this to be on, but I want to have a central location where I'm going to have all of my repos stored. Central location locally, not on GitHub. Central location locally where I'm going to have all of my repos stored. And what I wanted to do is I wanted to create a workflow where I store the repo on these on like in that central location, and anytime I need to work, I I do work on a local copy. So after storing it in that central location, I'm gonna clone the thing, and that will be my local working copy. So this what I have right now, this is my main repo and also the working copy. What I want is that I want the main repo to be elsewhere. And that's just going to be a bare bones repo. Fortunately, bare bones Git, it lets you create what's called a bare repository. It's a bare bones repository. Um, and you can use that to store your entire repo. Um, the difference between that and this is that that is apparently not a working copy. All that's storing is a compressed version of all of your it's storing a compressed version of your entire repo, your working copy, but like you can't really work on that copy. And it's also storing, all of the past commits and all of that stuff. So your entire repo is stored there, but in a very packed, very compressed form, which makes it so it's not occupying way too much space, which is great, right? Because if this repo ends up being, let's say, a couple hundred MB um, in size, if it's a couple hundred MB in size, and I want to create like a central repo for this. I don't want the working copy to also be a couple hundred MB, but then the main repo is also a couple hundred MB. And if I do this on the same machine, then now for each of these repos, I'm occupying like double the space. Fortunately, that's not the case. With a bare bones repository or with a bare repository, you're mainly just using it for storage. You're not working with that. If you want to work with that, you have to clone that repo, so you can then get a working copy. Though I should read up on that more to understand like what exactly is going on. I was having a conversation with Gemini about this to better understand, what how everything is working. And Gemini is the one that explained to me that this copy it's much smaller usually than your working copy, and the reason is because you don't have a working copy there. This is a very compressed version. It's not meant for you to work on. It's just meant to be a backup. It's just meant to be a storage kind of thing, and you can clone from this, but you can't really work on this. Though the interesting thing is you can't work on this directly, but I'm pretty sure you can push, because you have to push changes to the main repo, right? To the central repo. So you can actually push changes. You can also pull changes, assuming you have multiple clones. But you can't directly work on the repo. So I found that interesting. But yeah, this is what made me think about remotes again. Actually, no, there's one more thing. Um, in addition to this, so I wanted to make it so I have two main repos. I have a main repo stored locally, And then additionally, I'll also store it on GitHub if it's one of those tools that I want to share on GitHub. Then what I want to do is I want to add two remotes and make it so anytime I push a change, it pushes to both of the remotes. So it pushes to, the local central repo, and it also pushes to the repo that's up on GitHub. And there's a bit of a workflow. Um, there's a bit of a workflow to that. There's a bit of a workflow that I had to set up or figure out when it came to making Git and GitHub work together. It's not a very complex workflow, but there is a bit of a workflow that I had to figure out. Um, so yeah, that's kind of why I want to explore the concept of remotes again. I don't plan on going like too deep into stuff like looking into something like stashing, for example. um, there's rewriting history and stuff like that. I, I don't plan on looking into that stuff just yet because I haven't, like, dude, Git is an incredibly sophisticated tool. There's a lot of stuff that you can do with it, and it is sophisticated enough that massive teams are able to use it for various purposes. There are people who are dedicated to who have like a dedicated role of managing the repo itself. That's how sophisticated things can get, um, which is not a bad thing. It means that you can do a lot of very complex things with it. You're not limited to just doing simple things. You can set up very complex workflows using Git. For my purposes, though, because I'm the only person working on this, I only need the simple stuff, and so I want to learn all of the simple stuff and then just move on to working on things because I want to refresh my knowledge of Git and make Git a part of my regular workflow so that whenever I create a project that I'm working on, save I'll save the changes that I'm making to the project each time that I make the changes. Give me a second here. Let me That's just something that I'm doing. Okay, also let me hydrate and then I'll continue reading. Yeah, I guess today's stream we'll just keep it about Git. I was planning on doing this reading off stream anyways. But I guess I'll do it on stream now. Oh yeah. I am planning on reading, right? So let's do this. I guess I can, for the sake of letting my other machine rest a little bit, I'll stop the RTMP feed or, freeze the RTMP feed so the matrix rain will freeze. Um, Give me a second. Actually, hold on. Okay, let's get back to this and okay, all right. Yeah. So, here's what we're gonna do. Today we're just gonna read up on Git basics and kind of refresh our knowledge of Git. Something else that I learned is that okay, in this where was it? Recording about version control. Let's look at each of these pages because there was a very useful diagram that explained things. Um, let's go into chapters. A short history of Git, recording changes. Let's see if it's in here. Right, it's here. There was a diagram. There was a diagram that showed that what Git does, the way that Git works, is that it doesn't record the entire file. It doesn't store the entire file as part of, the new commit. What it's storing is the well, okay, what was explained was that each time that there's a change, it records the change and stores the change instead. So it's recording whatever the difference is between, the old version and the new version, and it's storing that difference. That is how, commits are able to be so small. But then Gemini told me that it's not exactly that. It's kind of the other way around because what apparently what really happens is that it stores the latest version of the file, and for all previous versions it stores the delta. It stores the change between this version and whatever that version was. I need to look into because Gemini also mentioned that in the pack files or packed files, I don't remember which one it was, but Gemini had mentioned that in the pack files it stores it in this way where it's actually no, hold on, I'm gonna open up that conversation. It was a very informative conversation. I got to learn a lot from it. um Hold on. uh Git, wait, I'm having trouble finding the conversation now. Okay, okay, no, where is it gone? Is it this? Right, we have this. And then I asked, okay, I guess I'll just open a new conversation with Gemini and get that information again. Sorry, I was trying to get the information so I can give you, the accurate version of it. Um, but then I can't find that information. Okay, we are dropping frames. Yep, we are dropping frames. All right. Okay. Hey, so help me understand how Git is storing the changes. because I remember in another convo you had mentioned to me that um, Git stores the latest version of the file, but then stores, but then, oh, stores the latest version of the file for the latest commit, but then for the previous commits, it just stores um, it it calculates a sort of reverse delta and only stores that delta information. So while Gemini gives me this response, I'll mention what Gemini said the reasoning was. It was that if you store the initial version of the file, and further from that point you only store the changes that have been made to the file, then anytime you wanted to look at the changes or let's say maybe clone the repo, I guess. I can't think of good examples to give here, but like anytime you wanted to look at, let's say, the most recent commit, because it's only been storing changes from the very first commit, let's say you have, I don't know, 500 commits so far, okay? It would then have to calculate 500 deltas for that one file, or 499 deltas, I guess. So if it was happening in that way, it would have to calculate way too much each time you wanted to do something. Um, so a good way to optimize that is to do it the other way around. We store the recent version of the file, and we calculate the reverse delta. So we calculate the delta in the opposite direction. So what would the difference be between the current version of the file and the previous version of the file? And then we store that difference in the previous, we store the difference of the previous version of the file as part of the other commit. Another thing I wanted to understand was how I'm supposed to be visualizing all of these commits. Because like all I can think of is like, okay, it's like a database, essentially. A database containing multiple commits, and each of those commits points to like um a different version. There was, oh yeah, I did ask Gemini how data was being stored, and Gemini mentioned something about there being a bunch of different trees. For each directory, it creates a tree, and if there's subdirectories, then there's trees for each of those subdirectories as well. And then there's like there's words. Holy shit! There's like a pointer pointing to um the other tree if there's like a subdirectory kind of thing going on. Okay, Gemini responded. It sounds like we might have had a slight wires crossed moment in our last chat. It's a very common misconception because logically, saving only the changes seems like the most efficient way to do things. However, Git actually does something more intelligent and robust. Okay, I think Gemini is about to give some new information. Snapshots, not deltas. The most important thing to understand is that Git thinks in snapshots. When you make a commit, Git doesn't look at a file and say, okay, the user added 2 lines here. Instead, it takes a picture of what all your files look like at the exact moment. If a file has changed, then Git saves a completely new copy of that file called a blob. Okay, I'm slowly remembering the concept of blobs. If a file has not changed, if a file has not changed, it doesn't waste space. It simply creates a link or a pointer back to the previous version of that file. Uh, Back to the previous version of that file it already has stored. Okay, where the deltas actually happen. You aren't totally off base with the delta concept. you're just thinking of pack files. To save disk space, Git eventually realizes that storing 5 full versions of a 10 MB text file where only one word changed is inefficient. Every so often, it performs a repacking process. It looks for files that are very similar to each other. It compresses. You know what? Ignore all the stuff that I said previously about how Git is storing the the deltas and stuff, because I feel like I need to uh, read up on this a bit more and get a proper understanding. Because I've either Gemini gave wrong information or I understood wrong from the right information that Gemini gave. Um, because back this was what 2, 3, 4 days back maybe when I'd had this conversation with Gemini, it made a lot more sense at the time. So I can't remember if I'm just remembering wrong right now. You know what? We could probably read this page and learn from this, right? Dude, there was a diagram that was showing it. I need to look. Oh, was it here? Okay, okay, okay. Let's go next. A short history of Git. Okay. What is Git? This was where I'd gotten that information. Let me show you the what do you call it? White page, light page, light screen, light theme. Um, light theme version of this. Um, so this is how I had gotten it. It stores like, okay, file A, file B, file C, but then it's only storing like the changes. Each time that there's a change, it stores the change. If there's no change, it just stores a pointer to, the file. You know what? No. Let's scratch out all the stuff that I was saying previously because I've got my information mixed up. You know what? You know what we're gonna do? We are gonna read. We're gonna we're gonna read. We're gonna relearn Git in how much ever time we have left now. We're gonna read up on Git again. Okay. All right. Getting started about version control. Actually, I don't think I need to read this because I know about version control and why version control is necessary. I understand this part already. Um, a short history of Git. As with many great things in life, Git began with a bit of creative destruction and fiery controversy. The Linux kernel is an open source project of fairly large scope. During the early years of the Linux kernel maintenance, which was 1991 to 2002, changes to the software were passed around as patches and archived files. In 2002, the Linux kernel project began using a proprietary DVCS called BitKeeper. In 2005, the relationship between the community that developed the Linux kernel and the commercial company that developed BitKeeper broke down, and the tool's free of charge status was revoked. This prompted the Linux community, the Linux development community, and in particular Linus, the creator of Linux, to develop their own tool based on some of the lessons they learned while using BitKeeper. Some of the goals of the new system were as follows: speed, simple design, strong support for non-linear development, so thousands of parallel branches, fully distributed, and able to handle large projects um, like the Linux kernel efficiently. I think I have a good title to give today's stream. Give me a second. Give me a second. I need to rename Um, Wait, how do I do? Is this actually going to be saved in that? I'm gonna okay. I'm gonna rename the stream from here, and later on I'll copy this. Um, Watch me get um get wrong and then get good. Oh, actually, watch me get wrong and then get good. Okay. All right. So back to this. Since its birth in 2005, Git has evolved and matured to be easy to use and yet retain these initial qualities. It's amazingly fast, it's very efficient with large projects, and it has an incredible branching system for nonlinear development. Okay, great. Okay, getting started. What is Git? What is Git in a nutshell? This is an important section to absorb because if you understand what Git is and the fundamentals of how it works, then using Git effectively will probably be much easier for you. As you learn Git, try to clear your mind of the things you may know about other other VCSs such as CVS, subversion or such as CVS, subversion or Perforce. Okay. Doing so will help you avoid subtle confusion when using the tool. Even though Git's user interface is fairly similar to these other VCSs, Git stores and thinks about information in a very different way. And understanding these differences will help you avoid becoming confused while using it. All right. Okay, snapshots, not differences. The major difference between Git and other VC. Hold on. Hold on. Oh God. I got this part wrong. Oh my God, dude, I remember reading this. I remember reading this because it says here Git doesn't think of or store its data this way. Instead, Git thinks in so and so. I got that part completely wrong. Holy shit. What did they say Git? You know what? Learning experience. Learning experience. Okay, let's continue here. The major difference between Git and any other VCS is the way that Git thinks about its data. Conceptually, most other systems store information as a list of file-based changes. These other systems, CVS, Subversion, Perforce, and so on, think of information they store as a set of files and the changes made to each file over time. This is commonly described as a delta-based version. All right. Okay. Git doesn't think of its file. Git doesn't think of or store its data this way. Instead, Git thinks of its data more like a series of snapshots of a miniature file system. Okay. With Git, every commit, with Git, every time you commit or save the state of your project, Git basically takes a picture of what all your files look like at the moment and stores a reference to that snapshot. To be efficient, if files have not changed, Git stores the file again. What? Git doesn't. Git doesn't store the file again. Just a link to the previous identical file it has already stored. Git thinks of Git thinks about its data more like a stream of snapshots. Okay. So between version 1 and version 2, let's say we have file A. So we have A1 and B is just a link to B. So that's why there's this dotted kind of thing. Wait, for the sake of looking at this properly, yeah. So we have this dotted kind of thing. So file A and C have changed. So we are storing the changes. We are not storing the changes. We are storing the new version of this file. Okay. How does it keep things small though? Because where does that reverse delta thing come in? I need to figure that out because even in this way, if we are doing it in this way, like, hold on, let's go back and read that again. With Git, every time you commit or save the state of your project, Git basically takes a picture of what all your files look like at that moment and stores a reference to that snapshot. To be efficient, if files have not to be efficient, if files have not changed, Git doesn't store the file again. Just a link to the previous identical file it has already stored. Git thinks about its data more like a stream of snapshots. Okay, this is an important distinction between Git and nearly all other VCSs. It makes Git reconsider um, almost every aspect of version control that most other systems copied from the previous generation. Wait, where was I? From the previous generation. This makes Git more like a mini file system with some incredibly powerful tools built on top of it, rather than simply a VCS. We'll explore some of the benefits you gain from thinking of your data this way when we cover Git branching. All right, nearly every operation is local. Most operations in Git need only local files and resources to operate. Generally, no information is needed from another computer on your network. If you're used to a CVCS, where most operations have a network latency overhead, this aspect of Git will make you think that the gods of speed have blessed Git with unworldly powers. Okay, because you have the entire history of the project right here on your local disk, most operations seem almost instantaneous. Okay, okay. For example, to browse the history of the project, Git doesn't go out Git doesn't go out to the server to get the history and display it for you. It simply reads it. What is going on, dude? I'm not able to read. Kind of ironic that I'm reading something. Okay, it simply reads it directly from your local database. This means you see the project history almost instantly. If you want to see the changes introduced between the current version of a file and a file over a month ago, Git can look up the file a month ago and do a local difference calculation instead of having to ask a remote server to do it or pull an older version of the file from the remote server to do it locally. This also means that there's very little you can't do if you're offline or off VPN. If you get on an airplane or train and want to do a little work, you can commit happily to your local copy, remember, until you get a network connection to upload. If you go home and you can't get your VPN client working properly, you can still work. In many other systems, doing so is impossible or painful, either impossible or painful. In Perforce, for example, you can't do much when you aren't connected to the server. In Subversion and CVCS, you can edit files, but you can't commit changes to your database because your database is offline. You This may not seem like a huge deal, but you may be surprised by what a big difference it can make. Okay, Git has integrity. Everything. Wait, before we continue, hey, I'm learning about Git. I'm kind of confused about how Git goes about storing um, storing changes or commits. What I'm reading so far is that Git takes a snapshot of what all the files look like, which I'm not sure if it's a snapshot of uh, if it's a snapshot for each file or one snapshot representing all the files, but also I don't really understand what a snapshot is. Okay, takes a snapshot of what all the files look like, and if a file hasn't been changed, it just stores a pointer. Git. Let's say Git just stores a pointer to that file in the commit. But I don't really understand how things are being stored. I had this conversation with Gemini previously in that time where I got some information from Gemini and got information that apparently I got wrong as well. Um, I need to rewatch today's VOD and give me a second. Yeah, I need to rewatch today's VOD and see if because I can barely remember what I was saying about Git and the stuff that how things are working because I'd read this, I'd gotten a solid understanding, and then now I'm kind of confused about like what I understood and whether I understood right or wrong. The reverse delta thing, I still need to look that up because the reverse delta. Okay, hold on. I'm going to read this. Snapshots, not deltas. The most important thing to understand is that Git thinks in snapshots. When you make a commit, Git doesn't look at a file and say, okay, the user added 2 lines here. Instead, it takes a picture of what all your files look like at that exact moment. If a file has changed, then Git saves a completely new copy of that file called a blob. If a file has not changed, Git doesn't waste space. It simply creates a link or a pointer back to the previous version of that file it already has stored. Then, where the deltas actually happen, you aren't totally off base with the delta concept. You're just thinking of pack files. To save disk space, Git eventually realizes that storing 5 full versions of a 10 MB text file where only one word changed. Oh my God. Hold on. I'm having trouble reading. To save disk space, Git eventually realizes that storing 5 full versions of a 10 MB text file where only one word changed is inefficient. Every so often, when you run git gc or when you run git gc, Git performs a repacking process. It looks for files that are very similar to each other. It compresses them into a single file called a pack file. Inside the pack file, it saves one version in full and then stores the others as deltas. Oh, that's where deltas come in. That's where deltas come in. Okay, my bad. I got the deltas thing wrong. It was to do with pack files, and when it comes to Git storing information, it's something completely different. The way that Git is storing information, it's completely different. Yeah, I got that part wrong. We're gonna explore this more in the next stream as well, because I wanna continue with relearning Git. Hopefully tomorrow's stream is gonna be the only other Git stream, because I just want to like refresh my knowledge of um honestly, okay, this what I'm doing, it's just for my it's just for my information. This specific thing, like learning how Git stores information, is just for my understanding. Um, in case if I'm ever wondering in the future how Git is storing this information, in case if I, get that sudden curiosity, then I'll be able to remember that, oh yeah, this is how it stores it, this is what it does, and so on. This information, it is not very important to me relearning some of the stuff that I came back to, learn over here. What we are trying to learn here is okay, this part, yes, this is going to be necessary, like learning the states. So your working directory, your staging area, where if um, if files have changed, then they're going to be in the staging area. I don't know if the staging area includes both the unstaged files and the staged files, or if it's only the staged files. I'm gonna have to look into that. Okay, it mentions here, staged means that oh wait, Git has three main states that your files can reside in: modified, staged, and committed. Sorry, these are not the three states. The three states are modified, staged, and committed. Okay, stage fixes and then commit. Oh, commit happens after stage. So this is the staged files. These are all the staged files. Okay, all right. So yeah, this part we need to learn. And then we go on to the command line. That is not necessary for now because we are not doing command line stuff. Uh, Further from this point, I need to go into, we can look into recording changes, just in case there's, some useful information in there. A lot of this stuff is being done via the CLI, so through commands. But then we are going to be using um, Git UI, just you know because we can, because like that's much more convenient. Um, okay, then we have viewing the commit history, undoing things, working with remotes. Okay, so we have the concept of remotes. We're going to look into that. We also need to look into this, into the branching thing. We need to explore branching again because branching does come up in multiple situations, or at least I've seen it come up in multiple situations. One such situation was um, when I was trying to make a contribution to a GitHub repo. I had to fork the repo first, and I think I had to create my own branch there. I think so. I don't remember that part. But once I made my changes and then I created a pull request, the pull request was supposed to be merged as a branch. So that's how it shows up, as like, merging the pull request. So we need to relearn this part as well, because Okay, first of all, yeah, I would want to be able to do it locally with my own, with my own projects, but also remotely if I want to like push something to someone else's repo, if I want to make a contribution to somebody's repo, then I want to know that, you know, I want to know what I'm doing if I ever need to do that again. Because throughout that entire time, Gemini was the one guiding me. I didn't know what workflow I was supposed to use, because I knew that, okay, I have to fork the repo and then make my changes. Okay, fine. Okay, I don't think I had to make my own branch. I don't think so. I don't remember actually if I had to make my own branch or not, because I had my working copy and I made changes to it, and then I submitted a pull request to the original repo where it shows up as a branch, and if the maintainer decides to merge it, then it shows up as, so and so branch is being merged into main. Yeah, I need to revisit that entire workflow again because I don't remember any of it. But yeah, yeah. Um, okay, yeah. Back to what I was reading here. Inside the pack file is where it stores the delta. The twist, paradoxically, Git usually stores the latest version of the file as the full blob and the older versions as deltas. Why? Because you are most likely to check out the latest code. This was where earlier when I earlier when I was explaining that thing about, having the later commit, this is what I was talking about. So this is why it stores. But then, okay, now this raises the question that when Git is storing these files, like at what point is the unpacking happening, or at what point is the unpacking system being used, and at what point is the snapshot system being used? I need to understand that part. Okay, further on, Gemini mentioned the three main objects. To keep track of all of this, Git uses a simple content addressable storage system. Everything is stored in the .git slash objects folder, based on a SHA-1 hash of the content. Okay. Um, so we have a blob. This stores the actual content of the file. No file name, just data. We have a tree, which is like a directory. It maps file names to blobs and tells Git which files belong together. And then we have the commit. This points to a specific tree. This points to a specific tree and contains the metadata such as the author, the date, the message, and the parent commit. Okay, all right. I feel like I still don't fully understand like how all of this is being stored. Yeah, let me say that. Um, yes, this has cleared the confusion that I had. Um, However, I'm realizing that I still don't really understand how Git. Actually, this might be answered in the other in the other conversation that I was having with Gemini. Yeah, it's mentioning the anatomy of a commit. Where does the blob come in here? Dude, you know what I'm thinking? If we are going to be doing this on stream tomorrow, I think I'll pause this here and I'll not continue doing this off stream. I'll dedicate tomorrow's entire stream to just doing Git stuff. Um, yeah, yeah. I'll dedicate tomorrow's stream to just relearning Git stuff, and also we'll continue these conversations. I the reason I'm doing this is because I want to get back to reading the Forrest Mims book because I've kind of pushed that to the side, and I don't want to push that to the side. Yeah, yeah. Oh, sorry, I was looking at something. Um, yeah. Okay. How Git efficiently stores so and so. Okay, wait. Um, I'm realizing that I still don't really understand how Git really stores all these different versions or different commits that we make. I'm not able to, no, I guess I don't fully understand the the connection. No, I don't fully understand how commits, blobs, trees, um, and even pack files um, work together, and at what point is what being used. Okay, it's helpful. It's words. Holy shit. It's helpful to think of Git not as a complex version control system, but as a very simple file system that lives inside your project. To see how these pieces work together, let's follow the life cycle of a single change from your keyboard to the Git database. Okay, this should be interesting. The loose object phase, commit time. When you first run git add, so that's our staging, and git commit, which is our committing, Git creates loose objects. It doesn't care about deltas yet. It wants speed and data integrity. The blob. Git takes your file, compresses it, and calculates a unique SHA-1 hash, which is a 40 character ID. This saves, this saves? It saves. It saves this as a blob. It it compresses the file and calculates a file hash, and then it saves this as a blob. If you have two identical files with different names, Git only stores one blob. Okay, okay, it stores one blob. Then oh, the tree points to a blob. The tree points to a blob. Okay, so the next thing we have is the tree. Git creates a tree object that lists the file names in your folder and points to the SHA-1 hashes of the blobs. Okay, all right. So the tree is pointing to the hashes of the blobs. This is how Git knows which file content belongs to which file name. All right, the commit. Git creates a commit object. This points to a tree and the parent commit. All right. At this stage, if you change one line in a 1 MB file, Git stores the new 1 MB blob. This sounds like it would get huge quickly, which leads us to the next phase. the pack file phase. Okay, efficiency time. Git eventually realizes that storing full copies of files that are 99% identical is a waste of space. It runs a process called garbage collection. During this phase, Git moves loose objects into pack files. This is where the magic happens. Delta compression. Git compares the blobs. It keeps the most recent version of a file. Oh, hold on. So it's storing a snapshot. It's storing a snapshot. Is a snapshot multiple things? Is a snapshot the commit and the tree and the blobs that are being formed from each of these files? Um, yeah, I think, okay, hold on. This is really interesting. Okay, I'm going to reread this tomorrow. I'm going to reread this tomorrow so we can. Wait, okay. Okay, what part of this? I'm just going to ask this question so, tomorrow we can continue reading this. What part of this is considered a snapshot? The snapshot is a conceptual state of your entire project at the specific point in time, at a specific point in time, represented by the commit and its corresponding tree. While we often talk about snapshots as if they are a single photo, in Git's internal database, a snapshot is actually a collection of pointers. Oh, that's it. It's a collection of pointers. Okay. Here's exactly what constitutes a snapshot: the integrity of a snapshot, the commit object, the tree object, and the blobs. Okay. Okay. Wait. So for each commit, I'm gonna ask all of these questions, and tomorrow we're gonna revisit like this whole conversation again. Um, Wait. So for each commit, it creates for each commit, if a file has changed, Git creates a blob of it, and if not, then it stores a pointer. Uh, so the tree would also have a pointer then, a pointer to the previous commit, a pointer to um, a blob from the previous commit. Also, um, is the blob basically just the compressed version of the file? And um, are the blob and file hash slash blob hash stored together? So, whole bunch of questions here, but that is going to be it for today's stream. I'm going to stop it here. I'm not going to continue reading this because there's a whole bunch that we have to read. I'm going to continue reading this tomorrow, and we're going to continue relearning, I guess, Git again. We need to read this stuff and then eventually get to branching and remotes. These are two very important topics for me. We don't need to worry too much about any of this stuff because I'm doing it over SSH using the bare bones Git repo. So we should be fine on that front. It's just mainly the branching and remotes thing that I want to focus on for now. So that's going to be it for today's stream. I'm going to continue now reading the Forrest Mims book. I'm also going to go back to trying to understand how electrons, protons, and neutrons work together, what states they are in usually when they're not, um, pulling and pushing and stuff, and how they together make up the surface that they are representing, and all of that stuff. I want to understand that before I move on to silicone, because in silicone there's information that builds on top of this information, this very basic information about atoms and the proton and electron and neutron. The silicone stuff builds on top of this. So I would like to understand this properly before I move on to that. But that being said, that's going to be it for today's stream. I hope you guys have a nice day, and I'll see you all next time. Peace.